we finish at here. We finish at this stage that we realize the transfer function from the error to the disturbance of the system is equal to minus ys over ws, which y is the output of the system and w is the disturbance to the system. Why es is equal to minus ys? Because rs is 0 based on superposition principle. So if we assume that the transfer function es over ws or y minus ys over ws is equal to tws. Tws is a given name for the transfer function from the output to disturbance input. In similar way, we define the system type for the with respect to the reference input. We can define the reference type, the system type for the subject to the disturbance. The system is type 0 if the response subject to the step disturbance input is a non-zero constant value. Okay? So based on the type again, using the type system type, we can have a rough estimation of steady state error based on the type of the input. Doesn't matter, this type is the reference or disturbance. Again, the system type is the one for the disturbance input if the steady state error for the ramp input is a non-zero constant, for the step input is 0, for the higher order is infinite. Now, we want to see how we can define the system type of a system subject to the disturbance input. We know, hopefully know, the system type from the reference, from the output to the reference input. We know how to define the system type. If you look at the lecture note, not last week, the week before, I gave you a table. In the table, I defined the position constant, velocity constant, and acceleration constant. Acceleration constant is for type 2 system, velocity constant is for system type 1, and position constant is for the system type 0. The same way, in similar way, I want to define the system type subject to the disturbance input. If I define the transfer function tw, which is minus ys over ws, as multiplication of two transfer functions, one s power n and another one TOWS. If my transfer function from output to the input to disturbance input is in this form, I can define the proper system type for the system. Again, using the final value theorem, the steady state y or the steady state error. Again, y steady state error is equal to steady state response. Y steady state error is equal to steady state response. RS is 0. Why RS is 0?
It's trying to maintain a steady output against disturbances.
But we are looking for the disturbance input. Look, the definition of the steady state is always the same. Doesn't matter which input are you looking for. You are looking for. Error is always R minus Y. Okay? If you're looking for transfer function or type system type from the output to reference input, it is this way, in this relation. If I'm looking for the steady state error from output to the disturbance input based on the superposition principle. I'm assuming R is 0. Still, the SDSS error is R minus 1. So I just need to put R equal to 0. Limit of based on the final value theorem when SDSS error is equal to limit of E when t goes to infinity. In this case, will be equal to limit of minus ys, yt, when t goes to infinity. That's why SDSS response is equal to SDSS error. Based on the final value theorem, I have the limit of SDSS error or response is limit of S TWS multiplied by 1 S power k plus 1 when S goes to 0. S comes from the final value theorem. TWS is my transfer function from the output to disturbance input. What is this? 1 over S power k plus 1? What's that? Is what? Is the disturbance input, exactly. Correct. Is the disturbance input. If k is equal to 0, I have STEP disturbance input. If k is equal to 1, I have the ramp disturbance input. If I do multiplication, this S will be cancelled with the 1 here, S1 here. So the limit will be limit of T O W when S goes to N over S power K when S goes to 0. What's the source of this S power N? What's the source of S power N? I didn't have S power N here. How did it come to the relation?
Oh, it's from the transfer function?
Which transfer function?
TWS?
Exactly. TWS, if you look at the previous slide, we define TWS as S power N TOW. So S power N TOW is TWS. Now you tell me, how can I define the system type for the such a system or such transfer function? What criteria should I look for? Or which values am I looking for? 3 type of the 3 values. 0, non-zero constant value, infinity. Okay? So, if the steady-state response or steady-state error subject to the disturbance is a non-zero constant, that's a type of the system. Look at here. If n is less than k, sorry, if n is bigger than k, what's the steady-state error? 0. If n is equal to k,
1.
not 1, is limit of TOW, which is a non-zero constant. If n is bigger than, is less than k, the steady-state error is infinite. Correct? So, look, how can I define the SDSS, the type of the system? This here is what we talk about. Sorry, what happened? Okay. So, as I said, if n is equal to k, the system type k is k, and the error is given by a non-zero constant. For example, if n is 1, k is 1, I have a non-zero constant SDSS response, which means the system type is 1. The system type is based on the order of n. If n is 0, for the n0, I have a non-zero constant SDSS error, the system type is 0. If for n equal to 1, I have non-zero SDSS, non-zero constant SDSS, the system type is 1 whatsoever. Okay? Is that clear to everyone? Yes?
Where does the, when you put TW equals
if you look
Yeah, I know it.
here, we define TW S power n as TOW.
Yeah, but on the next slide there's an S before the TW.
Okay, this is the final value theorem. What's the final value theorem says? Final value theorem says limit of f of t when t goes to infinity is equal to limit of s f of s when s goes to 0. So this s because of the final value theorem. Okay? Any question? So let's see these definitions based on an example. We want to, this is the satellite attitude control. We have a satellite, we want to control its attitude. The dynamic of a satellite can be shown by a 1 over j s multiplied to 1 over s in a very simple way. And I have a controller d of s. In forward, I have a unity feedback. Okay. Sorry, this is one is a unity feedback. You need to remove k. Or you can keep it because I have k here as well. Okay, doesn't matter. It is k and k. I can reshape this one as a unit feedback system. Why? Why this one is a unit feedback system?
The K's will cancel out. Yeah.
Exactly. I can bring k here, and this k will be cancelled out with the feedback k. Exactly. So I want to see the type of the system if I have the PD controller or I have PID controller. I will explain today what's the PD controller and what's the PID controller, just to have some idea. The shape of the PD controller is a constant gain plus constant gain multiplied to s, derivative part. But don't worry, I will explain. From this block diagram, quickly, tell me what's the system type of this system from output to reference. What?
Unity.
No, the system type. System type is 0, 1, 2, 3, 4.
0.
Any idea? 0, 2,
1.
1.
2. 2. That's great.
Who are agree with 2? Who says 2? Okay. Why 2?
1 over s squared.
Exactly. 1 over s squared because I have 2 poles at origin. What does it mean? No idea. Okay. What does it mean if I have the type 2 system? Okay.
What did he say there as a parabola?
Okay.
Or
Okay. This is for power or what?
for disturbance inputs?
No. We are looking for the output to reference input.
Oh, God.
Is 30% of your final project. Perfect response. Perfect. Perfect. I'm so happy. Great job. Great job. Well done. Look, without any calculation, I can say that since the system type is 2, or we have the type 2 system, if my input is a step input, a steady state error will be 0. If I have ramp input, the steady state error will be 0. If I have parabola input, a steady state error is non-zero constant, still constant. But if I have higher order system, the steady state error will be infinite. Okay? Without any calculation, just by looking at the transfer function of the system. At the end of the class, let me know your name. Okay. So, as you see, type is 2 with respect to reference input. But we are looking for as well the output to the disturbance. We always want to have the steady state error 0 with respect to disturbance, because disturbance is unwanted signal and we need to reject it as much as possible. So it shouldn't affect in any way the steady state response of the system. If I look at the transfer function from the y to w, the transfer function is in the form of 1 over js squared plus kds plus kp. If I want to show the TW as a s power n TOW, there is no s power n in the numerator, which means n is equal to 0. N equal to 0 means system type is 0. System type 0 means for the step input, I have a non-zero steady state error, but for the higher order of the disturbance inputs, the steady state error will be infinite. So system is just kind of robust with respect to step input. If I have higher order system, the system is not anymore stable or well performing. So PD is not good for me here because I'm looking for the steady state error with respect to disturbance input. Now let's look at the PID controller. PID controller transfer function is in the form of Kp plus Ki over S plus Kds. I want to see how much is the steady state error with respect to disturbance. If I shape the transfer function, look, I have one S in numerator, which means the type of the system with respect to disturbance input is 1. So I have type 1 system, or system type 1. In this case, I have the 0 steady state for the step input. I have a non-zero constant steady state error for ramp input, but infinite steady state error for the higher order disturbance input. So I improve the steady state error of the system for a wider range of disturbance input. One step more robust to the disturbances. That's why PID is better in terms of the controlling the steady state error compared to the PD controller. Correct? No? You are better? What? Explanation. Okay. Look, I'm looking for the system type from with respect to disturbance input. If I use the PD controller, I don't have any S in the denominator. So system type is 0. When I have the system type 0, it means for the S-step input, I have a non-zero constant steady state error. For the higher order, the steady state error is infinite. If I use the PD controller. If I use the PID controller, I can increase the type of the system one more. I have the system type 1, which means for the S-step input, the steady state error is 0, which is perfect, what I'm looking for. For the ramp input, I have a non-zero constant. Is it acceptable? But for the higher order input, the steady state error is infinite, which means the controller is useless. Right? But fortunately for the satellite attitude control, most of the time you can, the disturbances are not higher than the ramp input. If you have a satellite attitude control, if you have a PD controller and you have the S-step disturbance, you have the sum of some kind of the error. But if you have the ramp input, your satellite is somewhere else, the signal you're getting something else. Okay? So that's why we need to know how the system is robust against the disturbances. as a summary, last week and 1 week before, I talked about the system type. System type is defined for a stable system, or generally they are defined for the stable system, and can be defined as when a stable system can be classified as a system type defined to be the degree of the polynomial or which the steady state system error is a non-zero constant. Is a very brief description or definition for the system type. What I have talked about it so far. If you look back to the lecture notes, you see what is this definition. But as a summary, as a definition of the system type. We can define the system type for 3 types of the inputs. What are these inputs? No, in general. We have 3 inputs to the system. A reference, disturbance, sensor noise. Exactly. So we have 3 systems: disturbance, and sensor noise, and reference. But in this module, I'm not going to talk about the sensor noise. So what we talked about is first system type with respect to reference inputs, which can be defined as only a polynomial of degree k reference input. The type is the largest value of k for which the steady state error is a constant. For example, if for the ramp input steady state is constant but not 0, the type of the system is 2. Is 1. If a steady state error for a ramp for the step input is constant, not 0, the type is 0. Okay, the order of the polynomial input polynomial. In similar way, system type respect to the disturbance input is the order of n. How many cores we have at origin, or how many s do we have in the denominator of the transfer function? If the order of s is 0, type 0. If s1, type 1, and whatsoever. Okay, any question? No? So far it was let me, if I have any example, no. It was the lecture for the last week. Now I will start the lecture this week. Okay, everyone. So let's start the lecture for today. So far, we discussed about the basic equation of controls. We talked about the system type. Please listen up, everyone. In continuation of the today's lecture, I will talk about the control of dynamic error by PID controller. And after finishing this topic, the second chapter of this module will be closed. And then I will start a new topic about system description in state space. Okay, what's a PID controller? All of you know, at least the name is familiar to you. The controller, the PID controller is composed of 3 items: proportional control, integral control, and derivative control. and input to this controller is the error of the system. The difference from output to the input. That's why we call it PID, proportional plus integral plus derivative controller. What's the purpose of adding these three elements together to have a ideal controller or a good controller? If you remove any part of this controller, you will have different controller. If you remove integral and derivative controller, you will just have a proportional controller, which is a very famous and most used controller in the industry. If you just use the KP and KI, you will have a PI controller. If you just use KP and KD, you will have a PD controller. If you use the all elements together, you have a PID controller. If I represent the controller in the Laplace domain, the format of the controller is in this form: Kp plus Ki over S plus Kds. As we discussed already, 1 over S is equivalent to integration in time domain, and the variable S is equivalent to the differentiation in time domain. Okay, so d over dt is S, K, and Ki 1 over S shows this integration, and Kp is a constant, is a Kp. So the output of the PID controller is US, the control action, and the input is error. So in the block diagram, if you have the unit feedback with the PID controller DS and plant GS, the input to this block DS is ES, and the output is US. Okay? In industry, we represent, this is the mathematical formulation or representation of PID controller, but in industry, we use the represent US and we factor out KP as 1 plus 1 over TIS plus TDS. The dimension of TI and TD both is the second time. It has a better understanding for the technician or control users who wants to tune the controller. 1 over Ti is the integrator reset, and Td is the differentiator time constant. It's an industrial representation of the PID, but it's not a big difference. In this module, mostly we work with this representation as a mechanical engineer. Okay, so the first part of the PID controller is proportional controller. We can use the proportional controller alone, standalone. So we can ignore integrator and derivative part in order to have the most basic controller. If I use just the proportional controller, the transfer function US over ES is DS, which is a KP, a constant. I will magnify ratio of the output over input by the constant gain KP. The block diagram of this controller is GS is the plant, can be anything. The controller is just constant KP, and we try to adjust E of S by KP. We want to minimize ES by KP. By adding just this simple controller, we can change the nature of the system, the closed loop system. We can improve steady state error or the dynamic of the system. How? Let's see. Assume I have a second order system. For example, a DC motor. GS is the plant. A controller, a system without controller. Has the transfer function, second order transfer function of K over S squared plus A1S plus A2. I don't care about the A1 and A2. For this system, what's the natural frequency of the system? Root what? Root A2, exactly. And what's the damping ratio? Omega n is root A2. And what's the zeta? Damping ratio? A1 over 2 root A2. Perfect. So, the natural frequency of the system is A2 and damping ratio is A1 over 2 root A2. For example, I have a system with low damping ratio. I want to improve the damping ratio of the system. Look, damping ratio and natural frequency is the nature of the system. You can, by hand, change the natural frequency of the electric motor, for example, or easily tune it. If you want to change the damping ratio of the electric motor, by itself you need to design a new electric motor. Okay? For example, you have an application, you need the electric motor for that. The cheapest one has a damping ratio of 0.1. You want to save the cost. You buy the cheapest one. But by designing a controller, proportional controller, you can somehow change the properties of the system or change the natural frequency or damping ratio of the system. Let's look at it how proportional controller can change the properties. So if I find the closed loop transfer function will be Ts and the Kp, Gs 1 plus Kp Gs. In order to see how gain, proportional gain, will change the dynamic of the system, I need to look at characteristic equation, which is 1 plus Kp Gs. If I put the 1 plus Kp Gs, the characteristic equation equal to 0, my new characteristic equation is S squared plus A1 S plus A2 plus K Kp. In this case, what's the natural frequency of the system? Yeah? Pardon?
How did you go from the first one?
How did I get to this one? Okay. I have Kp here, and I have K over S squared plus A1 S plus A2. Correct? Can you see it? Pardon? GS is K over S squared plus A1 S plus A2. Everybody can see the transfer function? Okay. So in this case, Ts is Kp K S squared plus A1 S plus A2 1 plus K Kp over S squared plus A1 S plus A2. Correct? Is that clear to you? So I will have K Kp over S squared plus A1 S plus A2. Common denominator here, I have the S squared plus A1 S plus A2 plus K Kp over S squared plus A1 S plus A2. This will be cancelled out with this one. So I have K Kp over S if I have just DC motor omega n was root A2 and damping ratio was A1 over 2 root A2. For the new one, what's the natural frequency of the system?
Root A2 plus KKP.
Omega n is root A2 plus K KP. And damping ratio A1 over root 2 root A2 plus K KP. Correct? If I change KP, if KP is 0, omega n is root A2. There is no controller, which is the same as the open loop system or system without controller. But by increasing Kp, I can increase the natural frequency of the system. Indirectly, I can affect the damping, change the damping ratio of the system. By increasing omega n, I will decrease the damping ratio of the system. If you get back to your lecture notes, to the second lecture, you see that by changing the damping ratio of the system, I will change the overshoot of the system. And by changing the natural frequency of the system, we can change rise time of the system. It was the rise time of the system. But you need to look at the lecture note. But the point is that if I improve the rising time, I will change the decrease the damping ratio of the system. It's not acceptable. If the overshoot is important for me, Kp enough is not working. The proportional controller is a good controller as long as our expectation from the controller is limited. You can increase the damping, the proportional controller sum by a limit value. If you increase it too much, damping ratio of the system will decrease and the system will go somehow will be unstable. Okay? So the proportional controller alone, its performance is limited, very limited. You can improve the steady state error of the system, but for sure you will damage the dynamic response of the system. For example, you will increase the overshoot of the system. If you don't care about the overshoot and you just care about steady state error, proportional control is fine. Again, if your gain margin of your system is infinite, what is the gain margin? Okay, we don't have time to discuss about the gain margin. Go back to your year 2 control module and look at the definition of the gain margin. But the gain margin in very simple way is not the value of the gain at which the system is stable. For example, gain margin is 100, means that for the gain k equal to 100, the system is stable. For the higher value of this value of the k, the system is unstable. Or we will have the roots in the right hand side. Look again, by changing the Kp, we will change the location of the poles of the system. Correct? Because for the second order system, the poles are what? S1 and 2 is minus zeta omega n plus minus roots 1 minus zeta squared omega n j. If I increase k, the damping ratio will be decreased. And the poles will move towards the imaginary axis. If I have the poles close to the imaginary axis, what's going to happen? Lecture 2 or 3. I will have very fast response with high overshoot. Okay? So that's why Kp performance or the proportional gain performance is very limited. So what we here talk about, as I said, if Kp is too large, the damping ratio will decrease and we will have a very oscillatory response. Okay. In order to improve the performance of proportional controller, we can add integrator part or integral part. What can I get by adding the integral part? By adding the integral part, I can improve significantly a steady state error of the system. But what can be damaged? The dynamic response of the system. For the integral controller, if I have a pure proportional controller with a steady state error, non-zero constant, if I add the integral controller, I can reduce the steady state error to 0, as we discussed right now. Okay? Because we are increasing the type of the system. We can reduce the steady state error to 0. But we make the system sluggish. We increase the, for example, rising time of the system. But this drawback can be overcome by the proportional controller. So we need to look for the proper proportional gain and integrator gain in order at the same time improve the steady state error and the dynamic of the system. Okay? If I have the integrator controller, the transfer function from US to DS will be Kp plus Ki over S. The integral controller has dynamic. What does it mean? What dynamics comes from this relation?
Yes.
Exactly, S, 1 over S. The reason that we use the Laplace transform is that to transform the dynamic or dynamic equation of the system to the Laplace domain by S. D over dt is equivalent to S. 1 over integration is equivalent to 1 over S. So the block diagram is in this format. Again, the main advantage of using integral controller is that make the error to a constant input go to 0 and for the disturbance goes to 0, but it cannot deal with the steady state error due to the sensor bias or due to the sensor noises. We didn't talk about the sensor noises or sensor bias. But keep in your mind, if you want to improve the steady state error of the system, it's good to use, we have to use the integral controller. If a steady state error is not important for us, there is no reason to use the integral controller. Just proportional controller or PD controller is enough. If a steady state controller, a steady state error is important for you, at least you need to have a PI controller. If the steady state error is not 0 for just using a proportional controller. There is another drawback with the integral controller. Anybody can tell me what's that? We have integral. What is it in integral? What is it in integration?
There's a hole on the y-axis. There's a pole of the origin, sorry.
Okay. So
So
what's that?
there's an extra 0. It's just no an extra column, right? Which means
Integration means summation. Correct?
Yeah.
So if I have a very small noises in my sensor bias or sensor noise, it starts accumulating the errors and make another error to the system. For example, I have this one. The error is 0. W is 0. Or let's say this way. R is the output is exactly the same as R. So steady state error, the error is what? Will be 0. But if I have some noises in feedback, very small noises. Error is almost zero, it's not exactly zero. But when it goes to integration, it starts accumulating this small error. But after a certain time, it will be a huge value. Will damage the performance of the system. That's why in reality, in practical case, you need to reset integration after a certain time in order to make sure that the BIOS has been removed from the controller. Okay, this is the practical issue of the integration. In theory, it's perfect. But in practical, because we have noises and BIOS, central BIOS, it will accumulate this BIOS or noise in the system. Okay, so now let's see how the proportional PI controller will affect the location of the pulse or the dynamic response of a closed loop system. If I add the KP, assume I have a first order system. If I formulate the transfer function of the closed loop system, I will have the second order system. Look, open loop system or not controlled system has a first order system, but when I use the PI controller in the closed loop system, I will have the second order transfer function. As you see, Kp will affect the damping ratio and Ki will affect the natural frequency of the system directly. So by changing Kp and Ki, I can adjust both natural frequency and damping ratio of the system. For example, if I increase Ki to improve the natural frequency of the system, I will decrease the damping ratio of the system. But I have one more degree of freedom by Kp. So I increase the Kp in order to increase the damping ratio of the system. So I can indirectly adjust both natural frequency of the system and damping ratio of the system. Is that clear to everyone? Okay. So here is what I define. Okay, if I have the second order system, what's going to happen? If I have the second order system and formulate the characteristic equation of the closed loop system, I can change the coefficient of the, I will have the third order system. I will have the third order system. I can adjust two coefficients of the polynomial, the characteristic equation. But I can't change the third coefficient. So again, PI controller will be, this performance will be limited. That's why I need to have a PID controller to work with the third coefficient as well. Okay, it depends on what type of the system, what order of the system you have. If you have the first order system, maybe P or PI is enough. If you have the second order system, PI or PID is enough. If you have the higher order system, you need to simplify your system to at least third order system or second order system to see how PID controller can improve the performance. How we can simplify our transfer function to the second order system? If you, for example, I have the fourth order transfer function, by looking at the location of the poles and zeros of the system. If two poles of the system is far away from the imaginary axis compared to the two others, so I can ignore those poles which are far away from the imaginary axis. And I will just consider the poles closer to the imaginary axis. Again, look at the third lecture note to see how the additional and poles will affect the response of the system and how can I simplify my transfer function to second or first order system or at this third order system. Okay, before going to the differential derivative part, let me give you some example how PID controller can work. I have posted this MATLAB code on Learn. Download it and try to play with it by yourself. But look, I have a first order transfer function, k over tau s plus 1. Okay, if you look at your lecture note, the first order system. I want to see how PI controller will affect the performance of the system with different gains. Okay, it's too slow. I have a step input. What's the reason it's too slow? Look, the first system, the first graph shows the response of the non-controlled system, which means I have Rs k over tau s plus 1 y. Okay, let's put it here. The first one is k over tau s plus 1, y, and r, which r is the step input. In reality, without control, I can't do anything with this transfer function because it's the nature of the plant, the system. If I have such a system, the response will be in this shape. But I want to have a better response. What do I mean by the better response? For example, I want to have a faster response. Here, come on, what's wrong with this one? Here, I just use the proportional controller. Ki is 0. Here, I have a Ki and Kp. The coefficient of the Ki is much bigger than Kp. Here, Ki and Kp are almost the same. PI controller. As you see, for the step input, the system without control, the rising time is almost 3 seconds. Okay? I don't have any overshoot anything because the system is time order 1. If I use just Kp, I make the system much faster. The raising time is almost 0.2 seconds or 20 milliseconds. But I have a steady state error. The error is almost 0.09. Okay, or 10% steady state error. If I use Ki much bigger than Kp, the steady state error will goes to 0. But I will add more dynamic to the system. I will increase overshoot. I don't want to have an overshoot, but I have the first order system. If you look at the proper design, come on. Okay, it's better. If I have a proper PI controller, the steady state error is 0. The system is much faster than the non-control system. That's why I need to use a controller. Look, proportional controller is not enough. If I don't care about the steady state error and I just want to make the system faster, proportional controller is enough. If I want to improve both steady state error and fast response, the lowest value for the rising time, the Kp and Ki equal to 10 is enough. Now let's look at another type of the input. I think the reason that this one is Okay, I need to stay wait to finish this simulation. Okay, any question? What time is it? What? Okay, we have some time. Okay, it's almost done. I know what's the reason of this. Okay, now for example, let's see what happened to response of the system if I have, for example, salted input. Salted. I use CL now. A combination of the ramp input and what happened? Just salted. Okay. Look, is another example. If I have a kind of the ramp input. Any question, guys? Yep.
So for the bottom one, why is it underneath the input?
Pardon?
All the others, like you see the line like going.
What do you mean? Which line?
The red one.
The red one, okay.
Yeah.
What's wrong with that?
Like the system, like the controller is reading it like underneath the line. Like does it make a difference? Like.
Okay, I'll let it finish. Let it finish. You will see how we can fix. Let me fix this. What happened? Is it working or not? I don't know why it's so slow. I think it's because of the internet speed. What? Maybe. I don't know. It was much faster than this one.
But saying to improve both the steady state error and
Dynamic response.
so reducing accomplishment.
No.
Rise time.
Right time, kind of the right time. But overshoot will be increased by the user. Okay, look, I have a sawtooth input. Is a ramp input again reset to the ramp input. when you look at the open loop system, the uncontrolled system, look, huge steady state error I have, and look how much time takes to reach to the input. The blue line is the input, and the red line is the output of the system. I always want to have exactly the response very close to the input, or exactly the same as the input to the system. If I just use the PI controller, the speed converging to the reference input is very good, but I have a steady state error. I can't do it, or I can't solve this issue without the integral controller. If I have a higher, larger gain for the integrator compared to the proportional controller, I will add overshoot or oscillation to the system, make the system oscillatory, which is not good. But if I properly design the Ki and Kp, I will have a very fast response to the reference input. But again, this is for the type 1 system, system order 1. Sorry, the system order, first order system. If I have a higher order system, the performance of the PI controller will be more limited. Okay, do you need any break? Are you sure? Okay, 5 minutes. Just a moment. So teacher, just a moment, please. I need to take the video. Okay, it takes time. Go ahead. Right.
You asked me about
What's wrong with your?
I fell on it yesterday playing roller derby. So
Oh, okay.
I've had a drink. You asked Isaac you an email about the question in the coursework?
Okay.
About the U of, for the transfer function, do we derive it as if U of t was equal to 0? Or do we just take U of t out?
You need to take the UT out because you need first to look at the non-control system.
Okay, so that
See
transfer,
how the performance, and then talk about the U of
so
it.
that transfer function Z of S over Z of, Z of U over Z of R is assuming U is always 0.
Yeah.
Okay, right.
Then when you need to design the controller, you need to consider U. But I will tell you how.
Uncontrolled system is open loop system, or uncontrolled system is closed.
Loop is a slight different definition between the open loop control system and uncontrolled system. If you say the open loop control system, still you have the proportional gain for any kind of the control space. But there is no feedback. When I say uncontrolled, there is no just a flat.
This is a controller.
Yeah, this is the control.
Uncontrolled system is no control.
Exactly.
Oh, sorry. And I would ask
Just a moment, just a moment.